let's take a look at atomic structure. So in the 18th and 19th centuries, scientists developed and accepted the atomic theory. And the atomic theory was the idea that everything, all matter, is made up of tiny little things called atoms. Now, if you accept this atomic theory, you can explain a lot of phenomena that otherwise they weren't able to explain. So for example, the gas laws. You can explain the gas laws if you assume that the gas is made out of tiny little atoms, and those atoms interact in certain ways. This leads to molecular theory and leads to the kinetic theory of an ideal gas. And the atomic theory also explained a lot of chemical properties of substances. So the atomic theory was pretty well accepted by the time the 19th century was ending. But scientists started asking, is there anything more fundamental than this atom? Could you break open an atom and find little pieces inside? And in the late 1890s, J.J. Thomson answered that question when he discovered a very low-mass, negatively charged particle that exists inside of atoms. He named it the electron. Now remember, at this time, no one knew about a corresponding positively charged particle. They only knew about the electron. So J.J. Thomson's model of an atom was like this. He imagined the atom as being a spherical shape, spherical because it's nice and simple, and the electrons were inside of that sphere. Now electrons carried a negative charge, but most atoms had a neutral charge. So there had to be some kind of positive charge in the atom. Now he imagined that the positive charge was just an evenly distributed mist, or goo, that was spread throughout the volume of the atom. And this was known as the plum pudding model of the atom. Plum pudding because the pudding was like the positively charged goo, and the plums are like the little electrons that are embedded within the pudding. So this was the model that was common in the early 20th century. And then around 1909, a scientist by the name of Ernest Rutherford wanted to conduct an experiment. But he actually didn't want to do it himself because he thought it would be kind of boring. So he got his students, Geiger and Marsden, to do it for him. And this was the experiment. He wanted them to use a source of alpha particles. Now, alpha particles are positively charged, fast-moving particles. They didn't really know much about their nature, but they knew they were small, positively charged, and they moved very fast. So he wanted these alpha particles to be fired at a very thin sheet of metal. And Geiger and Marsden ended up using gold because it's very easy to turn gold into a very thin sheet. So Rutherford didn't think this would be very exciting. What he expected to happen was that these alpha particles would go into the gold foil, and the gold atoms, because gold atoms are really, in his mind, like the plum pudding model, they were positively charged mist with little electrons embedded inside. He expected the alpha particles to really just go through the atoms, to just pass through the positively charged mist and come through the other side barely affected by the whole thing. Again, he didn't think it would be very interesting. So Geiger and Marsden do the experiment. Takes a while, kind of frustrating to do, and their results were like this. They sent the alpha particles into the gold foil, and yeah, a lot of the alpha particles just went straight through. But some of them were deflected by a significant amount. And then, what was very strange, was some of the alpha particles actually bounced back from the atoms. And this is not to be expected, because if those atoms are made out of a little positively charged mist, the alpha particles should just go through it. They should not bounce back. Rutherford argued that in order to bounce back, the alpha particles must have encountered a relatively high mass, positively charged structure within the atom. And he argued that because those alpha particles, they didn't bounce back very often, they only rarely were hitting this high mass, positively charged structure. So this structure must be really, really tiny. So Rutherford developed the Rutherford model, and it was like this. The atom was still a roughly spherical shape. The electrons were still distributed around the volume of the sphere, but at the center was a relatively small, massive, positively charged part. Now, why is it at the center? Well, why not? That seemed to be the best place for it. And this small, massive, positively charged structure he called the nucleus. So there's mostly empty space, so most of the alpha particles that went through the atom were unaffected, which is what they observed. But every now and then, an alpha particle would get close to this positively charged center and would be deflected. So they saw some of the alpha particles being deflected by a significant amount. And occasionally an alpha particle would go right on target and get very close to the nucleus and be pushed back by that positively charged nucleus and go back in the direction that it came from. So in this view, the atom was mostly empty space. There was a high mass, positively charged center called a nucleus, and the electrons were just spread out in the remaining volume. So this did not explain everything. This was the model that explained the observations from the experiment. And this experiment was called either the Rutherford experiment, the Geiger-Marsden experiment, or the gold foil experiment. But it did not explain why the structure existed. It didn't explain why the electrons were on the outside. It seems like the electrons should be attracted to the positive charge in the nucleus and just go in there. It also didn't explain why the positive charge was collected in a nucleus. Shouldn't positive charges repel each other? Why is it all collected in one place? So it didn't answer everything, but it explained the observations. This type of observation, this type of investigation is called a scattering experiment. A scattering experiment is one where you have a target that you want to investigate, and you throw things at that target. And then by observing how those thrown objects are deflected and influenced by the target, you can learn about the nature of the target, the structure of the target. So here they were throwing alpha particles in towards the atom, and they learned about the structure of the atom based on how those alpha particles came out. This idea of a scattering experiment is very, very powerful in modern physics. This is the basis for particle physics, where we throw particles at other particles and we observe the outcome to learn about the inner structure of the particles. This is how the Large Hadron Collider works and other particle accelerators work. Now, later on, people discovered the neutron, and the neutron was found to be present inside the nucleus, and so they developed this concept of nucleon. A nucleon is any particle that exists within the nucleus. So both protons and neutrons are nucleons. There was also a lot of investigation into radioactivity at this time, and we'll talk about radioactivity later. Now, we have to develop a couple ideas here to deal with atomic ideas, and one is the idea of the element. So elements are defined by the number of protons they contain. Carbon, for example, contains 6 protons. If you have an atom that contains 6 protons, it is carbon. Uranium contains 92 protons. Hydrogen, 1 proton. Silicon, 14 protons. Iron, 26 protons. But each element has little variations called isotopes. And these isotopes are members of the same element with different numbers of neutrons. So, for example, if you have 6 protons and 5 neutrons, you're carbon, but you have a total of 11 nucleons. If you have 6 protons and 6 neutrons, you're still carbon because you have 6 protons, but you're a slightly different variation on carbon because you now have 12 nucleons. If you have 6 protons and 7 neutrons, you're still carbon, but you have 13 nucleons, and you have 6 protons and 8 neutrons. You have carbon, but it's 14 nucleons. Now, only one of these isotopes turns out to be stable. The other isotopes will decay. They're not going to stay as they are. They're going to change themselves into another form, which we'll talk about later. More about this stability idea in another time. Now, usually, the charge in an atom is balanced. Usually, an atom is neutral. So usually, a full atom contains an equal number of protons and electrons. So for example, if we have 6 protons and 6 neutrons in the nucleus, then we'd probably have 6 electrons in the outer part of the atom. If it's not balanced, then we call it an ion. So if you have 6 protons and 7 neutrons in the nucleus, but then you have 7 electrons in the outer part of the atom, you have an extra electron, so you have an extra negative charge, and this is called an ion. You could have 6 protons, 7 neutrons, and 5 electrons, and in that case you have a positively charged ion. Now, the standard way of describing an element is in this method. So if we have A and Z hanging on to a big X. So in this format, what we're saying, Z is the proton number, A is the nucleon number, and X would be the chemical symbol. So the chemical symbol is like C for carbon, N for nitrogen, O for oxygen, H for hydrogen, Au for gold, He for helium, Mg for magnesium, Fe for iron, and so on, just like you see in the periodic table. So for example, I would write a certain type of carbon this way. Carbon right here is C, 6 protons, has to have 6 protons if it's carbon, and then if I write a 12 up here, that's telling me the number of nucleons in that carbon atom. Now if there's 12 nucleons, let's see, 12 nucleons, there's 12 total protons and neutrons. And this number down here tells me that there's 6 protons. So let's see, if it's 12 nucleons, 6 protons, that means there has to be 6 neutrons. All right. I could also write this, uranium with 92 protons and 238 nucleons. Well, this tells me uranium always has 92 protons, but if it has 238 nucleons, that tells me that it has, let's see, how can I figure out the number of neutrons? Well, 238 nucleons minus 92 protons means there's 146 neutrons. And then if I have iron like this, iron has 26 protons, 56 nucleons. This type of iron has 30 neutrons. And the way that we say this out loud, this one would be carbon 12, this one would be uranium-238, and this one would be iron-56. That's the way it's usually said out loud. Now, over a couple hundred years, scientists observed unique behavior for elements. So for example, if you observe hydrogen, turns out hydrogen will emit visible light at 3 very specific wavelengths, at 434 nanometers, 486 nanometers, and 656 nanometers. If you observe helium, a different element, it emits visible light at different wavelengths. And if you observe carbon, it emits visible light at its own very specific wavelengths. Turns out, every element emits its own unique set of wavelengths. And it also turns out that each element will also absorb those same wavelengths. So every element has its own fingerprint of wavelengths that it absorbs and emits. And this leads to the idea of atomic spectra. So an emission spectrum, I'll draw them here. An emission spectrum is when you see the wavelengths that a specific element will emit. So for example, hydrogen emits 434 nanometers, 486 nanometers, and 656 nanometers. It turns out that is a purple color, a blue color, and a red color. So the spectrum would look like this if it's laid out. Helium, it turns out, the wavelengths that are emitted are 2 bluish ones, a teal one, a yellow one, and a red one. So those 5 specific wavelengths are emitted only by helium. So what the heck causes this? Well, this leads to the idea of the Bohr model of the atom, which came after the Rutherford model. And in the Bohr model of the atom, we have the nucleus at the center with its high mass and positive charge. But on the outside, the electrons are not just randomly distributed. The electrons have only certain orbits, which are called energy levels, that they can exist in. The electron in the atom cannot exist between these levels. It can only exist on or in these levels. Now, why is that true? It wasn't known at first. This was just proposed to explain the observations. Because in this situation, the low energy orbits are closer to the nucleus, and the high energy orbits are further out. So an electron could exist here, it could exist here, it could exist here, but it cannot exist here. Not allowed. And in this model, if an electron moves or jumps between levels, it has to change its energy. So if it jumps from this higher energy level to a lower energy level, then the electron lost energy. If it jumps from a lower energy level to a higher energy level, then the electron gained energy. Now, energy has to go somewhere. If it loses energy, then the energy has to be emitted somehow. So if it loses energy, the electron emits a bundle of light energy called a photon. Now, wait a minute. A bundle of light energy called a photon. But isn't light a wave? We saw back in waves that light is an electromagnetic wave. So how can we have a bundle of light energy? It needs to be a wave. Well, this is getting into a little bit of a deep topic, but we're going to conceive of the photon as a little wave packet, or almost like a little series of pulses. It's a localized wave. It's kind of straddling the boundary between wave and particle. And in this idea, that photon has this energy E, and that photon energy is equal to h times f, where h is something called Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds, and f is the frequency of the photon's light. And we can relate that to the wavelength, right, with c is equal to f times lambda. So in this Bohr model of the atom, the electrons can bounce between energy levels, but if the electron bounces to a lower energy level, it emits a photon. And if the electron jumps to a higher level, it had to absorb a photon of just the right energy. And the idea is that, for example, in hydrogen, the energy levels are just at the right points, where if an electron jumps from an upper level to a lower level, it will emit a photon with an energy and a frequency and a wavelength that corresponds exactly to one of the lines seen in the spectrum. The power of this, and the reason why this is important, is that if you were to look at a cloud of gas that's on the other side of the room, and it was emitting three specific wavelengths. Let's say you look at the gas and it's emitting 656 nanometers, 486 nanometers, and 434 nanometers. Then you know for a fact that that gas cloud contains hydrogen. What's really powerful about this is that imagine that the gas cloud is not across the room, but across on the other side of the galaxy. The idea still holds. If that gas cloud is emitting wavelengths of 434 nanometers, 486 nanometers, 656 nanometers, that means that that gas cloud includes hydrogen. And you've just figured out what the gas cloud is made of while staying on the other side of the galaxy.